Welcome back. In the previous part, we looked at the daily and annual motions of objects around the sky that are a consequence of the rotation and orbit of the Earth. Now we're going to look at some of the other motions in the sky that, while they share in the daily and annual motions, have most true motions all of their own that we can see in the sky. Let's start with our motions of our nearest celestial neighbor in space, the Moon. The Moon orbits around the Earth on an elliptical path that is tilted by 5 degrees with respect to the ecliptic. If we were to draw the Sun and Earth together like this with a line between them, representing the plane of the ecliptic, the Moon's orbit would be on another plane tilted by a small angle, 5 degrees relative to the Earth-Sun line or the ecliptic plane. The Moon's orbit is not a circular orbit centered on the Earth, but in fact is an elliptical orbit with the Earth located at one of the foci of the ellipse. The Moon gets as close as 363,300 kilometers to the Earth at a time called perigee, closest to Earth. It is moving fastest on its orbit when it is at perigee. Not just an illusion of being closer when it's moving, but actually physically moving faster at perigee. Why this is, we'll learn about later in the course. At the opposite side of the orbit, when the Moon is furthest from the Earth, it is about 405,500 kilometers from the center of the Earth. When the Moon is at apogee, furthest from the Earth, it is also moving physically slowest along its orbit. If I were to watch the motions of the Moon against the background of the stars, I would begin to be sensible of the fact that the Moon is moving at a slightly slower rate when it is further away and faster when it is closer. Now, having said that it is further and closer, you might think that it becomes immediately obvious when the Moon is close and far, but indeed, it's not obvious. In fact, it's very difficult to measure, and it's not even clear that this was visible in the ancient world. It certainly is visible and easily measurable today, but what is easy to measure today was not easy to measure 3,000 years ago. Despite the fact that the Moon is in an orbit that is elliptical, we can talk about the mean distance, the average distance that the Moon is from the Earth on at a given time, and that's a number which is 384,400 kilometers, or, to put it in proper perspective of scale, it is about 60 times the radius of the Earth. That said, you will notice that in all of my drawings here, the size of the Earth and the Moon have to be exaggerated in order for this motion to be visible on the small screen of our movie. If I drew everything to scale, you wouldn't be able to see anything. This is a common feature of this class. We're dealing with extremely large scales and extremely large contrasts of size and distance and time. And as a consequence, we're going to have to do a little bit of mental jujitsu here, changing the scale of things to make them visible, exaggerating sizes, shrinking distances artificially, just to bring them onto the same size. But always keep in the back of your mind, things are a lot bigger and a lot bigger contrast of sizes than we might expect. The Moon is closer at perigee and further away at apogee. An object that is closer to you appears physically larger in angular size. You'll see this in a couple of the labs that we're going to be doing coming up in the following week. If we take the difference in distance between perigee and apogee, the Moon appears approximately 11% larger at perigee than it does at apogee. This is a beautiful astrophotograph taken one half of a lunar orbit apart at different times, because we have the Moon full at different times, by the amateur astronomer Andrei Cudat. I'm sorry, Andrei, I can't ever pronounce your name. The picture on the left showing the Moon at perigee, perigee being closest to the Earth, and on the right, the Moon at apogee. These are the full Moon. These are taken many different lunations apart, showing the difference in size of the Moon. Shown on this high-resolution photograph, this looks really obvious, but in fact, it's not apparent to the naked eye, and it's actually quite difficult to measure because the Moon is just only barely resolvable by, the surface features of the Moon are barely resolvable by the eye. The human eye really only can resolve about 12 pieces, 12 pixels, if you will, across the diameter of the Moon. These photographs somewhat fool us because they're not what we can see, they're what a high-resolution camera can see. Again, another feature of this class that we'll introduce as an aside is beware of some of the photographs that we show and the images from space. While spectacular, they're not what the eye would see. The eye, while a marvelous instrument, is still limited in what it can do. And we've been able to extend the vision of our eye using optics, telescopes, and fancy detectors, both film and modern electronic detectors in the present day. What we can see of the moon, what is easily visible to the naked eye, and in fact has been visible through all of human history, are the phases of the moon, the changing appearance of the face of the moon as the Earth-Moon-Sun angle changes through the course of a lunar orbit. We know that, in fact, we have some of the earliest artifacts that are identifiable as astronomical artifacts are nearly 26,000 years old. A reindeer bone found in France on which one of our ancient ancestors carved out the cycle of phases of the moon. They're so distinctive in their shapes and sequence that we can recognize this separated by a gulf of 26,000 years. What are the phases of the moon? Well, the moon is a sphere. It is illuminated by the sun. It doesn't shine by its own light, but we see it by the reflected light of the sun. And if you illuminate a sphere from a distant light source, the sun, you will see only one half of that sphere illuminated at any given time, and the other half in darkness, the half of the sphere that is pointed away from the sun. As the moon orbits around the Earth, it changes the angle between the moon, the Earth, and the sun, and we see a different part, a different phase of this hemispherical illumination. What we see is the sunlight illuminated side, and the dark nighttime side of the moon is not visible to us. This full cycle of phases, which lasts from new moon to new moon, takes approximately 1 month. We call it a synodic month of 29.5 days. The word synodic comes from the Latin synod, meaning a coming together. In this case, it's a coming together of the sun and moon on the same side of the sky. This is not to say that the moon moves in front of the sun. It does every now and then, but not every month. So we have to keep track of where the moon is relative to the sun in the sky. Let's go through a series of phases of the moon and see how these look. Here we have a sketch now, grossly exaggerated scale for visibility, showing the cycle of lunar phases and labeling the 8 major phases of the moon. A cycle of lunation, a beginning of a synodic month, begins with new moon, when the sun, moon, and earth are along a line as shown here, with the moon roughly between the sun and the earth. Standing on the surface of the earth, the sunlit hemisphere of the moon is away from us, and therefore the moon is invisible. It is a new moon only when it becomes visible as it moves away from the exact sun-earth line. The moon, in this perspective, is moving around counterclockwise, as shown by the sweeping arrow. And so as the moon moves along its orbit around the Earth, it slowly moves out, and now we begin to see just a slight sliver of the sunlit hemisphere here appearing visible to us on the Earth. That part of the moon that's visible to us is the part that, in this sketch, is on the inside of the approximate circle of its orbit. I decided not to show the moon as an ellipse because that just sort of gets in the way. 1/4 of the way through a lunar orbit, the moon comes into this position where now the terminator, the dividing line between day and night on the moon, is pointing towards the Earth. As I look in the sky, I see half of the moon illuminated and the other half in darkness. Because I'm only seeing 1/4 of the surface of the moon illuminated, the other quarter that makes up the half illumination is pointed away from me at this time. I call this the first quarter moon. Sometimes we call it a first half moon, but in reality, we're only seeing a quarter of its surface. As the moon begins to move through the rest of its orbit, a larger and larger fraction of its surface begins to appear. We talk about the moon growing or waxing, to use an old English word for growing, until eventually the entire sunlit hemisphere of the moon is facing towards the Earth. As seen from the Earth, the moon will appear as a completely filled circle, and we say that we have a full moon. At this point, the orbital motion of the moon will now begin to take it around the other half of the circle, and we'll begin to see progressively less and less of the illuminated face of the moon, in which, to use again another Old English word, the moon is now waning. We go through a phase of waning gibbous. The moon is fat, gibbous, but not full, until we get to this position here, where the Sun-Earth-Moon angle is once again a right angle or 90 degrees, and we only see half of the illuminated moon. But now we see the other half that wasn't illuminated back at first quarter, and we call this the last quarter moon. As the moon continues along its 29.5-day cycle of lunation, we slowly wane to where we only see a thin crescent of the moon, and finally, 29.5 days after we began, we end up once again at new moon. This cycle of lunar phases can be seen from the surface of the Earth at various times, depending upon where we are during the course of this month. One of your exercises through this semester will be to start the practice of observing a cycle of lunar phases. It's an experiment that's going to take a little longer than one lunar month because the weather's sometimes pretty bad, and in order to see all the phases, you may have to observe a couple of cycles before you could fill in all the gaps. This movie shows the actual motions of the moon through one complete cycle of phases called a lunation. A couple of interesting features to note about this particular movie. First of all, you see the changing illuminated face, the shadow of the dark and light side from one side to another. But also you can see the moon growing in size. In this particular lunation movie, the moon just happened to be at perigee during full moon and near apogee during new moon. This doesn't happen every month. This was chosen as a very special time. The cycle of apogee and perigee and the cycle of the lunar months are not the same, but that's a much more complicated topic than I want to go into. You will also notice the moon is not just simply going in and out. It's actually sort of nodding a little bit, front and back, and kind of nodding a little bit left to right. You look a little bit, it's sort of doing a nod, like a person nodding its head up and down, and another motion of the head appearing to nod simultaneously left to right, like the moon was simultaneously slowly shaking its head left to right and nodding up and down. This shows you how really complicated the detailed motion of the moon is. This reflects a number of things. The elliptical orbit with different speeds, faster at perigee and slower at apogee, and the fact that we're standing on the Earth at a particular location and there are effects of what's called geometric parallax involved. These apparent nodding motions are referred to as librations, like the backwards rocking of a librum or a scale, giving them their name. The detailed motions of the moon are very complicated and well beyond the scope of this course to go into in detail, but needless to say, any good model trying to explain the motions of the moon must explain all of these motions in detail. This is one of the big challenges that met both our ancestors in trying to come up with a complete description of celestial motions. Now, when I said that this complete cycle of phases can be seen over the course of the month, when you see the moon during the day depends upon where we are in the midst of a lunar month. You don't see the full moon any old time of day, neither do you see crescent moons at any old time of day. When you see the particular phase of the moon, it correlates with an exactly particular time of day. Why? Because the cycle of phases of the moon is due to the combined motion of the Earth and moon system around the sun. And we're seeing the changing Sun-Earth-Moon angle. Let's take an example. Here's first quarter moon. The moon is at a position where the Sun-Earth-Moon angle forms a 90-degree angle. In this case, I've drawn the moon just a little bit before first quarter. At first quarter phase, the moon will appear to rise at noon and set at midnight and will be highest in the sky at sunset. We have to look at this from the perspective of a person not riding in space looking down on the system like our slides would imply, but a person like Brutus Buckeye here riding on the surface of the rotating and orbiting Earth. So let's start how this works. The sun in this view is off to the left, and we are at sunrise. The Earth is rotating counterclockwise, as shown by the red arrow, and the moon is orbiting around the Earth, also counterclockwise, as shown by the black arrow. Starting in the day, when Brutus is standing at this location here, sunrise is when we exactly cross over from darkness into light to the illuminated side of the Earth, and from Brutus's perspective, he sees the sun rising in the east. The moon is nowhere to be seen because the moon is in fact below Brutus's feet. If we wait a quarter of a day or 3 hours later, at noon, the sun is as high as it appears in the sky. I've shown here it looks like the sun is overhead, but that's just because I've had to flatten the perspective. The moon has moved a little bit in its orbit during that time, and Brutus, now looking off to the east, sees the moon just beginning to rise. But because the moon is only half illuminated, he only sees one half of the moon and says, aha, it's first quarter moon because I see a half illuminated moon rising at noon. 3 hours later, at sunset, the moon is now as high as it can be in the sky, and Brutus sees overhead a first quarter moon. Finally, at midnight, the sun is long since set, it's dark outside, and Brutus will see the first quarter moon setting way off into the west. So through the course of a day, Brutus here at first quarter moon will see the moon rise at noon, set at midnight, and be highest in his sky at sunset. And that would be true of an observer anywhere around the Earth during the time of first quarter moon. If we now go a quarter of a lunar orbit later to the time of full moon phase, we get a very different picture. Now we're going to start out at noon. The sun is highest in the sky as seen by Brutus, but the moon, which is fully illuminated by the sun here and fully illuminated hemisphere visible from someone on the Earth, is invisible to Brutus at this instant because the moon is below the ground. If we wait 3 hours later, when the sun is now setting, Brutus is passing from day to night, he looks off to the east, and as the sun is setting in the west, you see the full moon rising in the east. This is a characteristic of full moon phase. The moon rises while simultaneously the sun is setting. This is why you never see a full moon in daylight, and you only see it through the course of the entire night. If we wait another 3 hours later, at midnight, now Brutus is on the same side of the Earth as the moon, and the moon will appear high in the sky. It's moon noon from the perspective of a full moon. 3 hours later, Brutus is now passing from darkness into light. He sees the sun rising in the east, but the moon is now shifted around to his western horizon and is beginning to set. This is exactly this pattern of moonrise and moonset relative to sunrise and sunset changes for every one of the phases of the moon. One of the things you'll be doing in your moon observing exercise through this course will be to watch and record not only the position of the moon, but where you see it in the sky and the time of day you see it all matter. In particular, you want to watch out for where is the moon relative to the rising or setting sun, or is the sun even visible in the sky at all? This is going to help you trace out the relative positions of the sun, earth, and moon in space. As you watch through a course of lunation over one or two of these, start becoming a habitual moon observer, just like all of our ancestors were. You're going to start to actually see the celestial perspective of the Earth, sun, and moon in space. See if I'm not right when you try it. Now, I've only talked about the moon moving around the Earth, but in fact, the whole time the Earth is also orbiting around the sun. This is going to give us the first of the more complex compound motions that make up the motions of objects in the sky. The moon's motion against the background of stars, the way that we measure the positions on the celestial sphere, is far more complicated than I've led on to this point, because I've left out the part about the Earth moving. The moon's true motion is a compound motion of its orbit around the Earth and then the Earth's simultaneous orbit around the sun. If we start out here at the bottom at new moon at time t equals 0 days, then we have the Earth, the moon, and the sun all in a line, and new moon tells us the moon is between the Earth and the sun approximately. If I wait for the moon to complete one orbit with respect to the stars, that takes about 27.3 days, when the moon is now back around the circle, so it's gone around the circle and come to here. But in that same 27.3 days, the Earth has moved about 27 degrees along the full circle of its orbit around the sun. So now, when the moon comes back to the same position in the sky relative to the distant stars off in the far distance to the left, the sun is not in the same place anymore. And the moon actually has to move through another nearly 2 days, 2.2 days to be precise, to when it comes back into alignment with the sun and the Earth. This 29.5 days we've already met. That's the synodic month. It's the time from new moon to new moon. During the course of that 29.5 days, the Earth has moved 29 degrees along its orbit. About 1/12 of its orbit, a little bit less. Gee, that's about as long as a month, or 1/12 of a year. Is there a coincidence here? Of course. This is how we learn to tell time, by watching the motions of the moon in the sky. But you'll notice that new moon, the moon is in a different position on its orbit than it was here. For the moon to be back at the same position on its orbit isn't new moon 27.3 days later. It's, which phase? Well, it's shrinking in size because it's heading towards new moon, so it's waning, and we only see a tiny sliver, so that's waning crescent. So when the moon completes one orbit with respect to the stars, a sidereal or star month, derived from the Latin word sidus, meaning star, the moon has not gone through a full lunation. It's gone only through a partial cycle of phases. In order to go through a full cycle of phases, it and the Earth have to move an extra 2.2 days. This was observed. If you look at which phase the moon is in against the background stars, that changes from month to month, from lunation to lunation. This is reflecting the compound motion of the Earth-Moon system around the sun with the orbital motion of the moon around the Earth. This complexity of motion, again, requires explanation. It requires a self-consistent model to correctly predict what phase should the moon be in on a particular day of the month and against which stars should the moon be visible. These are not easy questions to answer, but they are repeatable over the course of many years and can be mapped out. This, in fact, was done by the earliest sky watchers of human history, and those records provided the essential data that allowed us to piece together the story of the motions of objects in the heavens. We've seen the motion of the sun and stars. We've seen the motion of the moon. Despite the complexities of the motion of the moon that I just described, when you come right down to it, the apparent motions of the sun, moon, and stars are relatively simple to describe. The motions of the planets, the other denizens of the nighttime sky, are far more complicated and defy simple descriptions. We can describe the motion of the moon in terms of a compound of two cycles, the lunar orbit and the Earth's orbit, but when it comes to the planets, it's not so simple. Why is that? Well, we're going to see. It turns out to not have a simple explanation. It took humankind nearly 5,000 years to find the right explanation, and that quest was the birth of science. The word planet comes from an ancient Greek word, asteres planetae, meaning the wandering stars. To the naked eye, you can't see the planets as disks, not like the moon and the sun. They're very different in their appearance. They appear like bright stars, and sometimes not very bright stars at all. For example, in January of the year 2015, if you were looking to the west-southwest, just after sunset, you would have seen the bright Venus, faint Mercury, and nearby the planet Mars, all in the sky together. It's a beautiful combination of objects, so remarkable it doesn't happen all the time that this particular news item from Sky and Telescope was put out. Look, you can see 3 planets all at once in the sunset sky. That doesn't happen all the time. Sometimes the sky can be pretty boring. Some nights at sunset, there aren't any planets visible at all. Other nights, you could see nearly all of the naked eye planets across the entire sky, across the ecliptic. Their positions move, and they move separate from each other. They don't move together, and they're not coordinated. But it's even stranger than that. The planets move relative to the stars in addition to rising in the east and setting in the west, but sometimes they change their directions of relative motion in complicated ways. For example, these are the motions of the planet Mars between September 24th, 1994 and July 4th, 1995. About 10 months of motion is represented here in this picture. The moon started out, Mars. Mars started out in September near the constellation of Gemini, the twins, and was moving in a general path, rising in the east and setting in the west, and started moving westward through the constellation of Cancer towards the constellation of Leo, which it reached by about the 2nd of January in 1995. But as it approached Leo, it was moving slower and slower, and on the 2nd of January it stopped, began moving in the opposite direction across the sky back towards Cancer, slowing down and stopping on the 24th of March, and then going back to its regular path, continuing along its way through the constellation of Leo through the time of July. This apparent backwards or retrograde motion is very difficult to explain. Here's that same motion now shown as a movie. It moves through the constellation of Cancer towards the constellation of Leo. As we come up on January, it slows. Well, hey, wait a minute. What are you moving the other way for? Moves backwards, stops, and then starts moving along its way again. Moving away until finally we'll stop the movie sometime around July 4th. Let's watch that again. The planet Mars is moving through the sky in its normal direction, but then starts to slow, comes to a stop, backs up, moves backwards for a while, faster, then slower, comes to a stop, and then resumes its normal path, getting faster and faster. That blip you see running through the sky there is the moon on the simulation done in Starry Night. What on earth is going on here? What we are seeing is retrograde motion. We are seeing the complex motion of the planets because we view them not from the comfortable perspective of a place in space looking down upon the solar system, but we are standing on a moving Earth which is also moving around the sun, and we're seeing the celestial traffic patterns of the planets in the solar system. So how do you explain these motions? How do you begin to use words to describe what we've just seen? Well, there are 2 basic ways we can come up with a description like this. The first we call a phenomenological description. We find a way to describe the motions without worrying about why they work the way they do. Just preserve the appearances. Get the description right. Get the words right. So say, yeah, well, it kind of moves to one way, stops, backs up, slows down, moves back again. Those are just words. They give a reasonably good description. They make good, reasonable predictions, but they don't get into the nitty-gritty of why it works that way. To describe why it works that way, we need to resort to a physical description. A physical description requires us to discover the underlying physical principles behind the motions, to answer the why does it move that way. In this case, the predictions follow not from geometrical descriptions, but from first physical principles. That's a much more difficult way of explaining the motions. A phenomenological description is just that, a description. A physical description is to build what we call a model, an actual explanation for the whys of the motion. How do we understand whether our description's any good? Well, any satisfactory explanation of planetary motions must be both internally consistent and it must have predictive power. It's not enough to get the answer right if you have to keep changing your model every now and then to meet each and every fact. That doesn't work. You have to come up with a single explanation that's internally consistent. You don't have to reach in and tweak the system constantly to make it work. The explanation must follow from a certain set of basic rules and follow those rules consistently time and time again. No cheating, no changing the rules, no special pleading to make things work out. If you've got to continually reach in and change the machinery to make your explanation work, it's probably not a very good explanation. The other feature it has to have is the explanation must be predictive. The explanations must measurably make accurate predictions of future behavior. It's not enough to describe what happened in the past correctly. You must also correctly predict how that system will behave moving forward into the future. The success or failure of your model will ride upon those observations. The observations of the past are used to build and test the model, but the predictions of the future are used to verify that model. Now, sometimes we do have to reach into our models and make modifications. We may have poor or insufficient data in the past, and so models are continually being refined by you adding new observations and adjusting those parameters that may have been poorly measured before. But that's not the same as internal inconsistency, because we haven't changed necessarily the machinery of the model. We've changed the speeds. We've made small changes in the motions. If I have to throw out the machinery entirely, perhaps that's what the observations are trying to tell us. The last thing you want to do is try to force the observations to match the machinery. That isn't fair. That's inconsistency. This is very difficult. For something like planetary motions, which play out over the course of year or years, you require observations of the sky that could span human generations, and you must bring together data that are good and data that are not so good and try to piece together from those observations a self-consistent, predictive picture of what's going on. That takes time, and in the case of the effort to explain planetary motions, it took us nearly 3,000 years from the first quantitative models of the ancient Greeks to the correct explanation in terms of the modern theory of gravity described by Isaac Newton a little over 300 years ago. Nearly 3,000 years of history to describe planetary motions. How did we get there? That will be the subject of the following lectures.